Managing uncertainty in projects. There are many methods for managing uncertainty in projects. There is a PERT method, project evaluation and review technique, that many operations management courses teach. And there are simulation applications where we try to determine project completion time or when activity times are random. A common misconception, especially in the PERT method, is that random activity times will cancel each other, meaning that, if one activity is long, the other might have a shorter than expected time, and overall, the expected time of the project will not be extended. However, this is actually incorrect in many cases, and here we will consider an example that illustrates this. So consider a project with just 3 activities, A1, A2, A3. A1 takes 3 or 7 days with 50-50 chance, so basically, right, 50% it will take 3 days and 50% it will take 7 days, no other probabilities. This is a bit artificial example, but bear with me. This is just for illustration purposes. A2 will take 2 or 6 days, again, 50% chance for each of those 2 times. And it's independent of A1, so it can be done in parallel. A3 will take 6 days always, so there's no uncertainty here, but it can only start after A1 and A2 are completed. So the network representation for this problem is shown in this little picture here, right? And you see that A1 is before A3 and A2 is before A3. And actually, I put here a solution for expected times. So if an activity takes 3 or 7 days with a 50% chance for each of those times, the expected time will be 0.5 times 3 plus 0.5 times 7. It will give me 5 days on average. The same thing here, the expectation for this random variable, 2 days with 50% chance or 6 days with 50% chance, will be 4 days, right? So if you put expected values and solve this project, right, you'll get 5, 0, 5 earliest times, 0 and 4 earliest finish times. So this will start at 5 at the earliest, plus 6, day 11. So it looks like expected completion of this project will be 11 days, right? So this is the summary of what I just said. Expected completion of the project is 11 days, and critical path is A1, A3, right? You will see slack here is 0, 0, and slack here is 1. However, in fact, when we consider exactly what is happening in this project, assuming the A1 and A2 are have random durations that are independent, there are really 4 scenarios that can happen, and those scenarios are summarized in this table here. So scenarios are both A1 and A2 will be late. They will take the longer time, 7 and 6. Or just A2 is late, or just A1 is late, or both of them are early, right? So we can have 7 and 6, 3 and 6, 7 and 2, and 3 and 2, basically all 4 combinations. Now, assuming these are independent events, the probabilities of each of those 4 events is joint probability, so 0.5 times 0.5, 50% times 50%. So probability of each of those possibilities is exactly 25%, right? What will happen then when both of those activities are late? This takes 7, this takes 6. The longer one is A1, so A1 will take 7 days, plus additional 6 days for A3. The total project will take 13 days, right? And A3 will start on day 7. Now, if A1 is early, it's not 7 days, it's 3. Then A2 here is late, it takes 6 days. The A3 can start on day 6, and the whole project will take 12 days. If, on the other hand, A1 is late, 7, and this one takes 2 days, it's the 7 that matters, right? So the project, the A3 will start on day 7 now at the earliest, and then completion of the project will be 13 days. And it's only good when both activities have the shorter times, 3 and 2, right? And in this case, the maximum of those 2 is 3, so A3 can start on day 3, and the project will take only 9 days. Now, what is then the expected completion time of the project? So I want you to see is that there are two cases when it finishes in 13 days. So expected project completion time can be calculated as right, two cases, each 25% chance. So I will put 0.5, 50% chance times 13, or let me put it like this, 13 plus 25% chance, it will be 12, right? That's our second scenario, and 25% chance times 9. So this is the calculation of expected project completion time. Now, if you do this calculation, you'll find out it's 11.75 days. So it's almost right? It's almost 1 day more, 3/4 of the day more than what we calculated just analyzing expected duration of each activity and then solving it as if this is a given exact, right? When we did a kind of review of all possible cases, so probabilistic analysis, right, we have expected time that is longer than the previous one. And what I want you to also see is that the critical path, in fact, actually shifts. Critical path shifts. What I mean by this is that here the critical path would be A1, A3. In this example, A1, A2, A3. In this example, A1, A3. And in this example, also A1, A3. So sometimes it is A1 that is critical, sometimes A2, and with unequal probabilities, right? So this would actually become even worse if I had more than two activities that are in parallel that have random events. If I had, let's say, 10 activities that are in parallel, then it's enough that just one of them takes long in order to delay the follower of those 10 activities, right? So so what I want you to see the conclusion from this, right? Remember, we started from the fact that random activity times will cancel each other out. No, this is not true, right? If you have especially a lot of parallelism in the project, the risk actually of running late is increased by this randomness, and the expected completion time is actually higher than one would think by looking just at activity expected times and solving the project this way. So rigorous analysis of a project like this requires something like Monte Carlo simulation. If you have more complex projects with a lot of randomness, running Monte Carlo simulation of a project can give you much better understanding of the distribution of project completion time, right? Which is so project completion time is a random variable. We just calculated here an expected value, and in this case, we calculated actually all possible final values. But if you have a complex project, you'll have a distribution of project completion times with many possible values and different probabilities, right? So Monte Carlo simulation is actually the best solution, and some simplified methods like paired analysis are actually not very good. They do underestimate the actual project completion time.